Okay, so we are going to talk about spectral learning of graphic models today. So I see fewer and fewer people stay, and the material is becoming more and more difficult. But luckily, I don't think we have. We may have more homeworks, but I don't really see a serious load on that because we've been talking about maybe spare you guys more time to the projects and that. So the content, in the last few lectures and the next few lectures are really, something that are not often taught in many different places. Okay, they are really quite fancy modern materials, not yet captured in any textbook. And whether they are useful or not, I don't know. I believe they are useful someday, but they are the frontier in graphic model research where people are still trying to identify good utilities. So in a sense, if you guys choose to follow up on some of these topics or do a project, not maybe here, but in the future, you are actually putting yourself right in the front of this line of research, such as the one you see today. So spectral learning of graphic models. You are going to see a kind of a totally different way of than what we see before in managing graphical models. So these type of models are particularly useful for dealing with latent variable models. Okay, so what are latent variable models? So this model, well, if I took all the edges on top of that, you see a HMM, right? So this is a basic latent variable model because you have these latent states controlling the emission of observations. And in fact, models people use to do natural language sentence parsing could be also a latent variable model where your observation is at the bottom layer, and then you want to parse it into different part of speech, and then you have this different parts being modeled as latent variable. And topic models, and very soon you probably will hear, actually you probably already heard these mixed membership models in general for network, topic, or image, is also a form of a latent variable model because the topic vector itself is not directly seen from the data. You need to infer that. So latent variable models are very useful in deriving semantic informations, from the data, and that's becoming very, very popular. But it happens with a huge cost because once you introduce latent variables, your likelihood calculation on data requires you to sum over all the latent variables. And that usually creates a non-convex loss function. Okay? And then when you solve the learning problem, that involves a non-convex optimization, and you get all sorts of troubles. So here I just want to make the example more explicit, but let's look at how people, for example, learn latent variable models. So here is a HMM, and the way you learn is to basically use an iterative procedure to impute these latent variables, right, based on what we know so far about the model. And then once you get all this imputed, what do? You treat them as if they are observed, and then you do the usual maximum likelihood estimation of parameters, right? For example, the transition probabilities between events. Well, events are not observed, but you impute them. Therefore, they become observed. And then also the emission probability can be computed in the same way. So this algorithm is known as a EM algorithm. It is used to optimize this, not this. This is the joint likelihood. The actual likelihood actually requires you to do a summation. Do I have an equation there? I don't. But if you want to do a likelihood estimation, P of x1, x5 requires you to sum over this whole thing, right? And that creates a non-convex problem. And you use a EM algorithm, as I just described, to do that. And the EM algorithm is a heuristic, as you know. There are limited guarantees on those algorithms. First of all, because the whole loss function here is non-convex, your EM algorithm can only guarantee you to converge to a local fixed point. Therefore, you have a local minima problem. And also, EM algorithm is very slow because you don't actually know how many iterations you have to execute. And also, in every iteration, you have to redo the inference problem of the latent variables. Right? So these are well-known problems in EM or in learning latent variable models. But the good thing is that it is very simple. You don't have to change anything in terms of the likelihood estimator. You just add a E step, which is the inference algorithm we learned before. So today we are going to actually do something very, very different. It actually start to look odd to you at the first sight. And in this particular framework called the Spectral Learning Framework, you actually have the so-called probable consistent learning, which means that once you have the data in place, you are going to learn the consistent model. And also, it is local minima free. It's very, very strange. How come a non-convex loss function become local minima free? And also, they are very, very fast. They are usually 1 or 2 orders of magnitude faster than the EM algorithm. Okay? And maybe even more magically, they don't have to rely on these parametric assumptions on models. Okay? Your transition probability from here to here does not have to be multinomial. Your emission from here to here does not have to be a Gaussian. They can be something very abstract, like what we learned in the previous 2 lectures, using a reproducing kernel Hilbert space embedding. You can basically introduce arbitrary local conditional probabilities, and that's also go very well with spectral learning. So how come there could be possibly such a method? Okay, that's something we need to actually discuss today. And the very high level bit of this message is that this particular paradigm of spectral learning is not an optimization procedure at all. Okay, it is not optimizing an explicit loss function. That's the very strange part of that. Therefore, you bypass this non-convex loss function due to the latent variables. Okay, you are going to only deal with the visible variables, but we are going to still make use of the insight, due to the latent variables, which is actually very important. Even if sometimes we don't operationally, work on that. Okay, all right, and there is a not so big but still quite interesting body of literatures on this topic. As you can see, the papers are pretty modern, right? They are no more than 3 or 4 years old, maybe 5 years old. And I welcome you to actually read all those and start kind of contributing to this literature, which is very young. All right. So one of the benefit, or maybe the trick that the spectral learning approach tries to benefit from is to re-examine the purpose of learning. Okay, this problem has been re-examined before. Remember in your 701 or 601 discussion, when we talk about naive Bayes versus logistic regression, you probably still remember there was this argument about which one is better, right? And one of the arguments that has been used is this so-called Vapnik's principle, where if your goal, for example, is to make a prediction from input to output, say this is y, this is x, then maybe you just need to learn a predictor, which is p of y given x. And you may not want to learn the joint of px and y and then compute a conditional of y given x. Right? That's kind of something you can do, which gets you this, but you paid extra cost in learning the joint sometimes. Right? So that means your learning sometimes need to be flexible in terms of what goal do you want to achieve. So in this case, latent variable models has many goals, and some of the goal can probably be achieved by a different learning paradigm. That's basically what the spectral algorithm was trying to exploit. For example, one of the major goals of learning the latent variable model is to make a prediction, right? You have this hidden Markov model. Your goal might be to predict what the next outcome is. Okay. Some people like to figure out what the latent state is. Say in the casino procedure, you want to predict what particular dice a guy used to generate what you see. Well, this is interesting, but utmost, I want to learn what's going to show up next time, and then I'm going to react maybe accordingly. Right? It's not the total goal of learning, but that's a legitimate goal. So if that's the case, then there might be a possibility to really build a model that directly connects you from here to here, instead of going through all these latent variables. Okay, and that's basically what the spectral learning algorithm is trying to look into and study in detail. So if you want to ignore these latent variables, just imagine you don't care about the semantics, don't care about the latent causes, you care about just a brute force prediction, then it is about really writing down the joint distribution of this whole thing, okay? And then if you imagine in the worst possible way, you express this as a big table. You can learn it actually from the data, right? And once you have this big table, you are going to now examine, okay, maybe this event equals to that, this event equals to that. I saw a few. Then I'm going to ask, what is the conditional probability of x 4 and 5 given little x1, little x2, little x3, right? So that's basically a particular query we sometimes would like to do, in many pragmatic systems. And this kind of query is particularly popular in industry, like in Facebook and in Google, and in those non-scientific places where my goal is for production. I really don't have an interest in looking into every tweet or every article to figure out what they really mean semantically. All I care is that whether the user is going to click on a button or not after doing so on and so forth, right? So in this case, maybe we do not even need to use a EM algorithm to figure out all these little things because they will be marginalized out when we do the prediction, right? And so in this case, can we just build a model that marginalizes out everything, and but starting from the latent variable model and marginalize out everything and make use of that? Well, then we need to ask what effect a marginalization could produce. When you look at this graphic model and you eliminate all these latent variables, what do you end up with? You end up with this, right? It's a clique. Basically, you are saying, everything become dependent of each other pairwisely, right? And if you really get into this space, well, it's unfortunate because you lose the insight semantically. But even if I don't lose insight, I lose a lot of computational resource because this is a complicated density function or joint distribution to represent, right? So you don't want to be there. So, and also, this marginalization does not factorize. Therefore, there is very little room for you to even take advantage of any computational trick reflected in these graphical models. All right. So, but HMM is different from a clique, right? So, and graphically it is different. But not only graphically or probabilistically, let's ask what numerically they can be different. That's actually where it gets you into looking at the graphic model from a algebraic perspective, not from a probabilistic or semantic perspective. This is actually a very interesting message. So let's maybe take one step back to look at even a simpler model, not a HMM, but this model. Okay, this is a latent variable model with one shared latent node and 3 observations. And just imagine each of these is a discrete variable, make it simple, of m states. Okay, so cardinality of that is 3. Okay, all right. So what if now let me ask you this funny question. Suppose that there are 3 nodes, and each of them had a state 3, has 3 m states. But I have a latent variable which contain 1 state. Okay, and what model you effectively have? Yeah, so this graphic model tells you this, which means that these 3 guys are conditionally independent given that. But now I tell you that H has 1 state. What kind of effective graphic model you end up with? The what?
They're marginally independent. It doesn't matter whether H is there or not.
They are marginally independent. Yes, that's correct. You get something like this. Why? Because regardless, this is a 3. Therefore, they can only, be, basically if you change this one doesn't get any influence because it doesn't change for anything here. It has only one state. Therefore, this guy failed to, channel the influence from other nodes, right? So this is one stream. You have a independent graphic model that contain one state that is totally independent. Now I ask the second question: what if H has m cube states? Okay, just exercise your imagination. This guy now has m cube number of states. And I still have this graphical model. So what this graph model effectively translates to. I encourage you to go to the other extreme. So one state gets you to here. If, I have m cube, of course, each of these has m state by themselves, then what this graph model should be equivalent to. Is that? It's a clique, right? It's a clique. Basic means that, with this being m, the joint distribution, any configurations can be realized, right? It means that any post combinations is actually remembered in here. And therefore, this guy, is not capturing any conditional independencies, right? Okay, so you're going to get something like this. Then the interesting question is why we need a latent variable model. Well, usually when you say a latent variable model, you should say these are maybe 3 states, 4 states, or 5 states. Somehow it gets you a reduction, okay, of the complexity so that you still have this graph over this graph. And the differences of this graph and that graph, as we reviewed in earlier representation of graph model, is that this one is representationally easier. You don't need to have the gigantic table. You basically have fewer number of parameters, meaning that some conditional independencies is there. Therefore, some particular configuration, doesn't have a meaningful probability, right? They still are possible, but they are the same probability as other configuration because there is a collapsing behavior. All right. So now let's ask, what do we expect to see when the number of latent states are in the middle? Okay. So this is actually the question we're going to ask today, like the spectrum view of the answer. All right. So you can imagine if you have something, in the middle, then you basically are, hopefully capturing some conditional independencies in the graphic model so that they still benefit from this graphical representation, but you save, in terms of representation cost. Okay. And so now let's see algebraically how can we achieve the same thing, okay, without using this latent variable. So here I achieve this by explicitly introduce a latent variable with a lower number of latent states. Now I tell you today that we have an alternative way of doing that by not even worry about latent variable models. We worry about only the observed variable, but still achieve that kind of reduction effect. So this is kind of the magic bits of spectrum learning. All right. Before I do that, let's review the algebraic rules of graphical models and expressed in matrix operations. This is the equation we discussed before. I just want to review that so that now let's remove from the graphical model kind of definition or language and start to stick to our linear algebraic language. Right? So in graphic model, we have this rule called the sum rule, which is a marginalization. And the marginalization in algebraic language is basically the product of two matrices. Actually, a product of a matrix times a vector. Okay? This vector is the marginal of y, and this is conditional of x given y. This is a matrix. This is a column. And when you put together, you get another column. So this is the sum rule. Right? When you use this dot product between a matrix and the vector, one dimension collapse. That effectively produces a summation effect. Okay? If you don't want to see the summation happen, such that you want to use the chain rule, which is symbolically also like this, but you don't actually get rid of the y. There is no summation in front to sum over all the y's. Then you have to put this y vector into a diagonal place of the matrix, and then you get a joint of x and y. Right? So this is how we now re-express the graphical model factor law with a number of linear algebraic operations. Okay? And we're going to stick to that now in the future. All right, so now let's look at what a graphical view about the graphical model tells us about what we just said about latent variables. Right? So here I have now I removed all the latent variables. I only care about the two observed random variables. And the minimum thing, or the most kind of the safest thing you can do is to write down a matrix of joint distribution. Right? So this is a matrix of m by m, let's say. Okay. And so what do we say? What can we say about this m by m matrix? Okay. One thing you can say is what if actually so this m by m in general, how much what's the rank of this matrix in the general case? Suppose you are allowed to put any numbers in here as long as they all sum to 1. What is the rank of this matrix? Mm-hmm. A minus 1. Why there is a minus 1 there? Well, it may be mysterious, but I would say m, right? It's a rank m matrix, right? All right. So in the general case, you have m. And just be careful what I said. I said you can put any numbers in here as long as they sum to 1. What does that mean? That means that all possible dependencies or independencies between these two variables can be taken care of, can be recorded or captured. Right? Now, if I actually assume that these two things, A and B, are independent, how do you expect the matrix to behave? Let's say this one, this model. What do we expect that matrix to look like? Diagonal? Why? Diagonal means what? It means that only they are equal to each other, you have a number. Otherwise, they don't have a number. That's not. That's too stringent, right?
Should look like the outer product of the variables.
I don't directly see that, but that's possible. I would suggest the following. It's basically like this, right? So now these two things are the same, are independent. Then you look at the one row in here. This basically is the row of being nailed down to one number, but the B being now changing from 1 to m. That's for sure. But because they are independent, I can re-express the rule as taking out P of A and multiply by P of B. Right? So basically, this is just a total factorization, meaning that P of A, B equals to P of A. Right? So this is what I mean by they are independent. Therefore, one row in here must be taking this form. What about the second row? Well, they will be probably P of A equals to 2 times everything here. Right? So you can see that every row is a linear transformation. It is just a multiplication of the other row. Right? And so this is strictly rank 1 matrix. See that? You have the same row, okay. Basically all the rows are multiples of just one of each other. Right? If you look at this is basically the vector of marginal of B, and then they multiply with a marginal of A. That's it. Right? So that's the extreme. If you have this A and B independent, algebraically or linear algebraically, that means their matrix of joint probability has rank 1. Okay? And just remember, here I have full rank, M, and here I have rank 1. Now you ask, what is in the middle? Okay? And that's the interesting thing to ask. Right? Let's say I have now a middle equal to K, smaller than M. And I claim that this guy is effectively equivalent to some hidden variables. Okay, they introduce some amount of conditional independencies, not to the extreme that they are making the things totally independent, and not to the other extreme that they are capturing all dependencies. Okay, so this is basically the linear algebraic view. Without explicitly introducing hidden variables, I can still create a joint distribution that bear the intrinsic low dimensionality nature of the joint distribution. Okay, by controlling the rank of the joint distribution. Okay, so that's actually a key thing that we want to remember. So you have this now, okay, the low rank structure, which is equivalent to introducing this hidden variable x, and depending on the rank of the x, okay, you actually get a variety of different effective rank of the joint distribution. Okay, are you with me so far? So hopefully this is intuitive. All right. So now I claim that suppose I'm not going to establish you a explicit dependencies. I'm going to introduce this x explicitly as a hidden variable, and it deseparates A and B. Remember, this graphic model translates to undirected and directed in the same way, right? And so I'm going to assume that x has its internal number of states, k. Okay, then I can show you that the rank of the marginal of A and B will be upper bounded by k. Okay, that's basically a property that you want to remember. That basically established the connection between the hidden variable with the hidden states and the low rank expression of the joint. And the proof is very simple, right? Based on the graphic model, you can always write down, linear algebraically the joint as the product of these three things. This is something we already explained in last lecture, okay? And now, you have x in all three matrices, and we said that the number of hidden states of x is k, right? And what does that translate to in these three matrices? So this one is, what is the rank of that? It could be at most k, right? If not fewer. If the two states are redundant, then they have fewer. What's the rank of this? It's basically x conditioning on A conditioning on x, and x has at least at most k states. Well, that gives this matrix at most rank k, right? Because there are basically only k conditions that you can use to write down the column and the rows. So anyway, because of this bottleneck in x, now your three matrices become rank constrained, and then their product will be also rank constrained. Therefore, the whole thing is also rank constrained. That's basically the proof. Okay. All right. So given that, I established hopefully a high-level picture about the equivalence of a low-rank linear algebraic expression of the distribution versus a latent variable model. And now let's see how can we actually do a paradigm shift and do graphic model learning and inference using the linear algebraic techniques. And we're going to use the following concepts a lot. And but we're going to actually see how much, what do you lose from this operation and what do you gain out of it. So let's now look at a more interesting example. And that one is getting you closer to the real graphic model. And once you know this, you can handle many other things. So again, we have a HMM now. Okay, and the observations are just the discrete states M. Okay, and the hidden states are K. The hidden variables has K states. And if I have 4 of them, just imagine I have a chunk of the chain in the middle. I want to write down a joint distribution of these 4. Okay, and therefore this is a big matrix. Okay, then I hope you already are convinced that this matrix has rank K. Do I need to prove that? Hopefully this is by intuition, right? In the previous slides, we already proved that if you have a hidden variable of state k, your whole thing will be also rank limited at k. And in this case, the only way that these things are connected is through the k, state hidden variable. Therefore, this whole thing also has rank k. Okay. And if you are curious, you can prove at home by factorizing this whole thing and identify the bottlenecks explicitly. All right. So now we have this matrix m by m. Let's talk about generic thing. Here I have m by m, but now let's talk about just an m by n matrix. Imagine arbitrary square matrix, rectangular matrix. If you were told that it has at most rank k, then you can always write a decomposition, right, in this form, a left matrix and a right matrix, right? And so this is a decomposition for a arbitrary rectangular matrix. But for our matrix, we can also write down the decomposition, right? At least we have one factorization we already know, which is this. This is the graphical model decomposition, right? You have we introduce the hidden variables, and given the hidden variables, you have the two states ahead of that, the hidden variable itself, and the other two states after that. That's one way of doing that. Now, this is a fact, but is it interesting? This is not quite interesting because this is no different from our original latent variable graphic models. You have everything, right? So you don't really gain anything rather than having some fancy notations. But notice that this decomposition does get things a little bit easier. Here, you start from a 4-variable big table of a likelihood. And here, each of the entity has a fewer number of variables, right? And that's actually one of our argument in graphic model, definition in the beginning. That factorization leads you to smaller building blocks, and you can see here. But these building blocks are not so ideal because some of the building blocks are defined on imaginary quantities, which are not observed, right? So this is where you want to hopefully ask, can we find an alternative way of doing this? So any insight from your linear algebraic knowledge on how this might be dealt with in a different way? For example, is a decomposition of a matrix invariant? Meaning that do I have only one composition for a matrix or do I have multiple? Right? So that's something you can ask. One thing you want to remember is that there is always this trick, in linear algebra that whenever you need some kind of variability, you can introduce something called, this dummy thing, identity matrix, which is produced by one matrix times its inverse. And then you can plug in here. Then you suddenly have an LA, and that gives you the same result. But your decomposition is different, right? So this is called the rotational invariance. Right? You are basically shifting the latent, bases, in terms of their orientation or somehow. All right. So let's try to see whether we can find an interesting alternative factorization. So interesting that the latent variable may be just eliminated. This is something very, very interesting. You want to find some nice way of writing this decomposition so that this h vanishes, so that your pieces are always dependent on the observed variables. Okay. So that's the second message in spectrum graphical model inferences. It is about finding this correct S. Okay. All right. So without telling you the S, let me show you first what an ideal factorization we probably would like to see. Okay. And then we're going to backtrack about that S. So this is our joint. And you can imagine I could gain already by making them, a combination of smaller building blocks of, maybe a joint of 3 random variables instead of 4. So maybe somewhere on the right-hand side, I should have these two things. Hopefully, right? All right, let's imagine that will happen, hopefully. But let's take a look about how these two pieces look like. okay, and how they can be further decomposed. Again, without using any linear algebraic insight, we just build on the graphic model insight with latent variables. We can say, well, introducing a latent variable pivots the whole thing into two parts, and then I can write down this decomposition generically. Right? So this is just conditional independence given latent variables. Okay, so now if you want to stare at these two equations, you might find something interesting. So suppose let's pick this piece, that piece, and this piece out. What do we get? Imagine we don't have these three things. We just have these three green pieces and multiply them together. What do we get? The whole joint, yes. And how about these three pieces? Well, this is the smaller joint of 2 and 3 only, right? All right. So that gives you somehow a hint. Somehow within the right-hand side of these two things, I have both this and that. So how about I do some really dirty trick? So let me do the following. I'm going to put a P of, P of x3 and h2 here, and the inverse of that. Okay, suppose I put this here. So I'm going to use this to cancel that piece, right? And in here, I'm going to put, P of x2 and h2 inverse. How about that? I'm going to cancel this, right? So now this one cancels that, and this one cancels that. I want to also put another thing. This is the diagonal h2 here. Okay. So imagine I just plug in these three things in here. What do I get? And I multiply these two things together. What do I get? Okay, so that's the tricky thing, right? So I'm basically left multiplying this part with this, and right multiplying this with that. So what I get is of course, I need to do the same thing also in here, right? So I need to do things here and also in here, and the things in here and also in here. So then you will see on the left-hand side, I have a P of x1, 2, and x3, and have this x3 given h2 inverse, and I have a P of diagonal h2 inverse, and I have a P of x2 given h2 inverse. That's basically what's going to happen on the right-hand side, left-hand side. On the right-hand side, what do you get? Anyone can help me just to read out these results? So this one cancels this, right? And that one cancels that. And then this one finally got to see this guy. They cancel each other. So on the right-hand side, what do I have? I have only the green stuff, right? And the green stuff equals to this, right? So I have now a factorization of this. Well, where does this come from? Well, I assume that there is a nice inversion law that, which is this guy inverse is defined by that guy. Okay, basically, I'm assuming that P of, I hate to write all this, but maybe I just want to make it more explicit. Okay. By the way, this equals to P of x3, x2 inverse by definition, right? This is by definition from here to here, right? Because that's what we define as the red stuff. And we now assume that this guy, the inverse of a product, equals to product of the inverse, right? Which is what you usually see in linear algebra. In fact, this can only hold under a condition of rank constraints, but we're going to mention that later. But this is pretty intuitive, hopefully, for you, right? So with that, we have now this guy. So this is a new factorization of the joint of 4. Now what you see, what you can tell from here, no latent variables. Okay, everything is observed. And the strange thing is that in our original factorization here, it's nice in the sense that every pieces in this factorization is probabilistically meaningful. It is a probabilistic entity of the joint, of the marginal, and so on and so forth. That's exactly what we used to insist on in the Bayesian network factorization. But in here, this new factorization is kind of strange. So this guy is statistically meaningful. It is a joint of the 3. And that guy is also the joint of another 3. What is this guy? This is the inverse of the joint of a pair. And that's basically a strange matrix with no statistical meaning, right? But the numerical benefit is that now you have 3 components that you can use to recover the joint of 4. And the 3 components are only depending on observed data, not hidden variables. And what you lose, of course, is some factors no longer are probabilistically meaningful. All right, are you still with me so far? All right, so hopefully this is straightforward. And so we achieved one thing. We achieved a factorization which now only builds on the observation. And again, the trick is that to introduce a latent variable to help your inference, and then there are pieces depending on here, depending on that, and there are some other pieces dependent on that in a different way. You can see that this is both basically happening on the right-hand side and the left-hand side of this pivot. Okay, but there is also another set which is the intersection of these 2 pieces. And there, of course, are other factorizations you can use. There's another one which are equally valid, and that gives you some different statistic if you care about in the inference. So this is not unique, but one thing that you want to remember, you want to hopefully see is that, in fact, before I talk about the relationship, if you are given such a factorization like this, what do you mean by learning now? When we say we learn graphic models, what are we learning if we are taking this representation as our paradigm? Well, you are going to only learn this table, and that table. And in this case, you learn it, and then you invert it, right? So this is a learning that is happening only on the observed random variable. You don't have to learn a thing called P of x1 and x3 and x2 given this. You don't have to do that anymore, right? This learning involves EM, and this learning involves nothing.
When you actually want to know what the so-called hidden states are, for example, in a lot of problems, you may want to know what a particular
then you lose.
State.
Then you pay cost. If you want to learn a hidden variable, this method is not useful, right? But I imagine there are many cases you don't want to learn, right? That's exactly the naive Bayes and the regression, the logistic regression argument, right? Basically, if you are willing to save, because remember, this computation is 2 orders of magnitude faster, okay? That's it's not a trivial game, okay? And if I tell you that, you can get this speed up, you have to worry, with yourself. Do you really need the extra expense and in return for something useful or not, right? And to my knowledge, most people, the hidden variables are not used. They just sit there. For example, in training topic models, what people use is I train a topic model, a big vector of a few thousand dimensions. You don't read it anymore. You basically directly put them into the input of another predictor and generate a 1-bit prediction on yes or no. And in that case, if you don't really care about the latent variable, you shouldn't really, probably spend time to infer that. Right. Again, this is just a matter of a taste, but now I told you, at least if you want to do this, how this can happen. So again, algebraically, it's interesting to at least understand the relationship between this factorization and the previous one, right? So here I have one decomposition, which is pretty standard and trivial. And I said that it is not unique, and you can always plug in a S. And now I tell you what that S corresponds to produce the previous decomposition that has only observed variables. So you can do some exercise. I could prove it to you online here to take one line of proof, but so this is the S, okay? And this is the resultant factorization it produces, okay? And this part is actually what the L times this S. L is basically this part. And I think you can immediately say that you see that these two pieces times this one will get you this. Right? It is the conditional of x12 given h, then marginal of h times conditional of x3 given h. And it is, in this case, a chain rule, not a sum rule. Actually, it is going to be a sum rule after all, because it is a chain rule in here, but then, when this one multiplies with this one, it is a sum rule. Right? Therefore, the little h is gone, and you get a marginal of this. Right? And these two actually correspond to that piece multiplied with this piece and some additional thing. And I want you to go home and derive that. Okay. I have it actually in the notes, but I'd rather not show it here. Okay, so after all, this fancy factorization is just a rotation of the original factorization based on the latent variable graphical model. But you get the game of eliminating the hidden variables. So this is not very amazing at this point, because you have 4 nodes now reducing to 3, not a big deal. But you can extrapolate this rule actually to a much, much bigger space, to the point that many graphic models can be recursively factorized into this form. Okay, for example, every latent tree, of v nodes can actually of this v variable can actually have the same factorization, okay, where every factor has a size of 3, okay, and all the factors are only a function of the observed variables. In fact, let me give you just maybe do I have one example here? No, I have actually one example later, but I will show you at least an insight about how this recursive decomposition happens. And that's going to make you a big deal, because then your very large-scale, graphic model with a lot of latent variables gets eventually boiled down to many, many multiplications of factors of size 3, okay, defined only on observed nodes. Okay, so at this point, I think we should be pretty clear about what we meant by learning and inference in this new paradigm. So this is the spectral learning paradigm, where the stuff we are interested in are this guy, not the hidden variables or the conditional probability given the hidden variables or the conditional probability between the hidden variables. Okay, it's directly these 3 entities, and one of them is non-probabilistic. And what you do is your training is going to giving you basically the maximum likelihood estimation of these 3 tables. How do you do that? Well, you directly count patterns from your data. This is not a big deal, not too many counts, because it's just 3 random variables. You basically collect these triplets and count their configuration and put them into this table. That's it. Right? In this case, you need to do another step of inversion. And in testing time, what you do is you are going to plug in your query into these tables. Say you want to learn the configuration or the likelihood of this configuration. Well, that basically translates to plug in or finding the right column and rows in those learned matrix and get things out. Okay. And so here is an example of generalizing with more variables. Now I have 5 random variables. Okay, and based on the same law I just used, I can now break them down into these 3 pieces, except that now on this far right end, I have a piece with 4 variables. Okay, and this guy can basically go further and gets further breaked. And now you can notice that this guy, everything is basically a function of only the observed random variables.
How do you deal with continuous rather than discrete random variables?
Good question. Remember our kernel trick? Right? So it's basically a kernel function. And I'm going to actually mention that in the last 2 or 3 slides. This whole thing is now a table. And when we talk about continuous, we're talking about functions. Right? And functions maps to table in terms of operators and feature mappings. Right? So everything you can replace, so this one, all can be replaced by joint operator, conditional operator, and the feature maps. Okay, so that's the magical part. Not only continuous, but even non-parametric distribution can be managed in the same way. Okay. All right. Consistency, that's coming automatically, right? Because we are doing, after all, maximum likelihood estimation of every smaller tables. Okay, and they are consistent due to the law of large numbers. So this is our earlier consistency. You want to, in a trivial case, just estimate the whole joint with the big table, and we don't like it because what if you have too many variables? So we use graphical model, and graphical model gave us this, introducing hidden variables, and then we got to now estimate smaller tables. This one, all are smaller. But we need to deal with latent variables, right? And but this case, it is still consistent, even though it is not attainable in many cases because of the local minima, right? So in this case, you are going to now do MLE of these 3, entity or 3 variable or 2 variable tables, and yes, they are also consistent. Okay, and also they are globally optimal because these are just one single step MLE with no latent variable involved. Okay. All right. So what is the catch now? So we know a linear algebraic way of dealing with graphic model learning and inferences, and we knew that it's going to get us away from the latent variable operation, such as EM. So we talk also about the intrinsic kind of utility of the latent variables, which is to partially capture the conditional independencies, in a sense to make our model simpler, right? So now we ask how that directly translates to the behavior of this, this linear algebraic operation. Does it, for example, allow you to go at the extreme of capturing all conditional independencies, or it gives you, some power in modeling conditional independencies? Okay. All right. So here, the way to examine that is to take a deeper look into this guy, because everything else seems to be pretty normal. It's nothing different from what you do in a fully observed model, and basically everything without a latent variable, without linear algebra operation can be, also captured in here. But this guy is very unique to our linear algebraic or spectral learning algorithm. So we haven't even talked about, does this guy exist or not? Right? Have you thought about any scenario this guy may not be existing? Symbolically, you can write anything, but does it really exist? For example, when you calculate P of x2 and x3, can you really invert it? That's actually the tricky question. Right. So worthwhile taking a look. So let's take a look. So when does the invert exist, right? Well, at least, based on the very definition of linear algebraic inversion law, if every, of these matrix are full rank and the square, then its inverse exists, right? Because that basically gives us the very definition of, you can basically invert every element of this and use the definition of the inverse of product to make it the product of the inverse, and then everything carries through because every single pieces can be inverted. Okay, So that's not really quite interesting because it pretty much means that this the rank in here is full. Therefore, the number of hidden states here must be the same as the hidden states, the states in here. You don't really benefit in any sense from the H. Usually, what we benefit is that either H, this K, is greater than, smaller than M, so that you get a reduction in terms of representation. Right? You have smaller states to capture some conditional independencies. Sometimes it makes sense to have K greater than M if your whole purpose is not about efficiency or about reasoning. Your whole purpose is about feature extraction. Look at the deep neural network. You have this tiny bottom layer, and then suddenly become very fat in the middle, with a lot of redundancy states. And that's for you to extract features. So these two ends are both interesting, right? And so making K and M equal is not very interesting. You basically are copying what you have in here to here. That's it. Right? Or maybe with a rotation. So now let's look at a case where M is greater than K, meaning that the degree of freedom in observation is greater than the degree of freedom of the latent variable. So in those cases, the inverse cannot exist. Okay, it is a rank deficient matrix. You cannot invert it. So this one cannot be inverted. But what you can do is to do a trick. So this is a P of x3, x2 and x3, which is in this case a M by M matrix, but with rank K. Therefore, you cannot invert it, right? What you do is you can now turn it into, you just do an eigenvalue decomposition of this and get the top left and the right singular value on the vector of this matrix, and then put the left one in here and put the right one in here. And what you get is basically a matrix of K and K. This is a rank K matrix, right? And the etc. K by K matrix of also full rank, that can be inverted, and then you're going to reassemble by multiplying back the V and W. That's kind of a pseudo inverse, right? So it can be happening, and you still get the right operation. So that's doable. Okay. The other case is a K greater than M. K greater than M, actually, in that case, this inversion also exists. Okay, say, I have this M by M matrix, but imagine there is a hidden variable with a K greater than even the M. I don't know how to write it down in here because here it has at most K rank, but the hidden variable, once you introduce that in, it blows up the whole thing even bigger. In that case, the inversion still exists, but it does not equal to this anymore. Okay, this very distribution law of the inverse no longer holds for this kind of matrix because every piece here may not be invertible. Okay, so in that case, it is very difficult to fix. We don't know how to do that. Okay, our pragmatic attitude is that let's ignore that. We don't care about any cases K greater than M. Okay, and again, this is for a practical reason as well. We are doing the prediction under a need for high efficiency. Therefore, we are not going to introduce redundant unnecessary states for deriving features because we don't need features. We are going to directly make the prediction based on observation, not even using any feature in latent space, right? And so, what if with such case happens? Suppose that I just gave you one scenario about the hidden states being more than the observation in deep neural network. Even in HMM, you can still run the same scenario. And here I have a generative model where, say, you are going to have two type of outcome, A and S. A is a repetitive character which can go anywhere from 1 to n times before you can stuck in a S, S being one of the two possible options, X and Y. And then you are going to introduce a hidden variable H to give rise to this guy. And then what do you need to remember? Well, you need to remember that in which of the possible n, how many times you already generate the a's. Okay, you need to remember anywhere from 1 to n. Then you need to also remember x and y being the choice. Right? So at the end of the day, you're going to produce sequences like this, and your number of latent states will be 2n. Right? N for each of the possible s character, and you have 2 of that. But your observation, what you're seeing here are still just 2 or 3 characters. Right? So your latent state can blow up very much, but your observation will be very small. So in that case, you create a scenario where latent states are more, and that's not very good for our model. Okay. But even in that case, we can do some practical trick. Okay. First of all, we only work on, this scenario work well, right? We can define, little factors depending on a few number of observations. But if you really have a bigger or long-term dependencies, so here basically the way you get things down to a manageable size is to only care about the so-called short-term dependencies, right? These 3 things are next to each other. Therefore, you don't need a lot of latent states to hopefully, take care of the latent complexity. And then you get this nice factorization. But if you really worry about a very long-term dependency, for example, you want to have some factor that captures this guy and something way ahead or something way after, instead of writing down a big table, remember the so-called conditional random field trick. We can build features directly, in a global sense. So we can basically introduce those features which are summarizing, the behavior of a longer subsequence, with the notion of long-term dependencies. Put it on the right and put it on the left. And operationally, it is not changing what we do. Okay, that's actually the trick in spectral learning. So look at this product of the joint of 2 variables, and symbolically, it equals to expectation of the outer product of 2 indicators, right? The indicator of x2 and the indicator of x3, and therefore you can express them as this, right? And now, if you are having, this is basically the basic feature, which is really indicating at that particular spot too what particular state take place. That's why it's called indicator function, right? But if you have a long-term, features of higher order dependencies, and therefore you replace them with a feature to the left and a feature to the right, then you just replace these basic features with my richer features, okay? And therefore, your factorization will go the way as it is, except now you are replacing the indicator feature with your richer feature. And when we say excitation, that means sample average. You just count, the number of times that particular feature configuration happens in your data. Okay. So this is pretty much the same as what you did in conditional random field, where you are going to compute the strength of every feature combinations. How many times the word ing, or the combination ing appeared in your category, in your vocabulary. How many times the word ixg, x being nothing, appeared. You can do that kind of feature counts. Okay. All right. With that, I think I showed you most of the basic tricks in spectral learning, and we can see some experimental evidence of this being hopefully a favorable alternative. I wouldn't say it better because it is unknown in a broader sense yet, but in some of the studies, such as I listed in here, there are good signs of its being quite favorable. So here, there are applications in a number of domains, including a particular project in my own group, where we just want to, replace what people usually do with latent variable models using EM, using the spectral approach. So here are the synthetic experiments where we generate the data from such latent variable models, latent tree models, latent HMM, HMM with higher order, and the factorial HMM, so on and so forth. You can generate all that. And in this case, for example, you probably know a factorial HMM is fairly complicated to infer because the latent variables had a complex state space. But now in our spectral learning algorithm, we really don't have to worry anything here, right? We only worry about all these little triplets to build our factors. And the training amounts to filling in an estimate of these factors or their inverse. And the testing means that you just plug in or pick the right column and rows from those learned matrices or the product of the learned matrices. Right? So without going to the details of the exact design of the experiment, here are some high-level kind of message that you can get from the pictures, from the performance curves. So one thing is about runtime, okay, in terms of the training cost. And of course, the costs go up with the amount of data. So we have the data samples here. I forgot the unit of that, maybe a K or something, but you can see the way it goes up. And you can see the EM algorithm. We actually compared the two benchmarks, okay, the EM algorithm and an online EM algorithm. What do we mean by online EM algorithm? Any guess? So EM algorithm is by definition a batch algorithm, right? So in the E step, you do inference on all the hidden variables, right, of every data points. And then on the M step, you collect all the sufficient statistics and update the parameters and go back and forth. Online means that you assume a streaming data setting. You start with a subset of data, okay? And when you do the E step, you estimate based on the current model on the next subset of data, okay? And then you keep updating your model, until you reach the end. It's usually quicker, but it doesn't necessarily. It's quicker in every iteration, but very often it takes more iteration to converge, because your data may direct you in different directions, okay, in every iteration. Anyway, so at the end of the day, you can see the difference in the time at least. So this is the complexity of spectral algorithm. And I told you there are 1 or 2 orders of magnitude differences, and that's where you'll see the EM algorithm. Performance-wise, they are roughly comparable. The spectral algorithm isn't significantly better, but they are about the same compared to EM. You can argue EM may be worse, but at least it's not significantly different. So that's basically a picture you can get in comparison in comparing these 2 alternative approaches. And I also have another example on the part of the parsing, supervised parsing of natural sentences. And the model used is a probabilistic context-free grammar, okay? And the probabilistic context-free grammar was usually a latent verbal model, and the training happens only at the bottom layer. But you can also get training labels in the middle layers to make the training more easy. But in any way, without getting the details, Shay Cohen, a postdoc previously was actually graduate from here, but now he's already a faculty. But when he did this work, he was a postdoc with Michael Collins in Columbia University, and you can see the numbers, right? So this is the performance, okay, in terms of the F1 bracketing score. I don't really know too much about the score means. I think the NLP people here probably know better than I do. And all I want to say is that their performance are comparable, okay, between EM and Spectral. But if you look at the time, okay, it takes to train the model, and you will see a difference. Here are in the order of minutes, and here are in the order of, I don't know, many, many hours. All right, so any questions so far? Yes?
So right at the beginning, you said something about how EM is prone to actually converge to local minima. How how is that reflected in the results where you actually get comparable results rather than actually better results for?
Yeah, so I don't know. I mean, EM is prone to local minimum. It's a theoretical observation. But when you actually run EM, what do? You actually run multiple times, right? Somehow, in this case, maybe they're lucky or whatever. Or maybe the model is not too complicated, not complicated enough yet, so that the performance advantage by skipping the local minimum isn't really reflected strongly here. But maybe I should make the following argument. If you run EM once and compare this one run once, then you can immediately see the difference already, because that one is unlikely to give you the optimal answer. Right? All right. So it's, in a sense, an unfair comparison already. You are running the EM algorithm multiple times, but of course you get more time as well for that. Right. Yes?
So is the computational expense of EM coming from running it multiple times?
I believe so, although I didn't check carefully. But I don't believe they run the EM algorithm, for example, 100 times. So therefore, we are still faster. Right? All right. So now the natural question is that, I show all the tabular distributions, which is kind of uninteresting. How can we get to continuous or even non-parametric ones? So here I just have a few slides to hopefully, point you to the right direction, right? So these are what we now want to care about, the latent states being something strange, the observations being also something also strange, if not more strange. And then we basically use this, the Hilbert space embedding, right? And then again, the whole thing can take place totally symbolically, because we already established the equivalence of a symbolic algebraic computation to the operators in the Hilbert space, right? So this one, as I mentioned before, is now taking expectation on the indicator features. We can blow them up with the real features, right? But still, it is an expectation. But in the Hilbert space, you can now replace this table. By the way, remember, this is still a table, right? But now we're talking about a functional mapping. Therefore, we can now define a covariant operator, right? And that basically is now the expectation of the transformed vector, in outer product of 2. And this transform vector now does not even have to be in the explicit form, right? Here, I kind of say you can design these two feature vectors and make them, into your equation. In here, this is becoming totally abstract. It is a feature vector in your, reproducing kernel Hilbert space, right? Therefore, it is not explicit. It's only becoming explicit when you multiply this guy with another guy to have a kernel function, and that's where you plug in the right number. So everything that we learned from kernel graphic models, from embedding of distributions into a kernel space, carries here, and all you do is to replace, the appropriate probabilistic entity with their corresponding operators. We have the covariant operator, and we have bigger operators in here, and that's basically how you start to handle, continuous and non-parametric space. All right, so I have another few minutes to summarize, which is great. So here is a side-by-side comparison now, okay, where you'll see the comparison between EM and the Spectral. By the way, here when I put Spectral, I really don't mean just the linear algebraic operation I put forth just now. Okay, it also includes the trick we learned in the previous lecture and last week about kernel embedding and the kernel operators. Okay, so the benefit is indicated in gray, in green font, and the deficiency, the caveat, or the pitfalls are in red. And you can see these two things are really complementary. Okay, they are almost exactly complementary. So you cannot find a domain where both are good, but it depends on your need. Unfortunately, I wish I could find something that combines the greens, but so far we don't know yet. So on EM, the great thing is that it is the so-called statistically efficient way of doing things, meaning that you have the off-the-table statistical interpretations. Okay, you know everything you are doing, and every intermediate or final product has a statistical interpretation. It could be latent variable, conditional distribution, or something like that, right? And in here, you are in the black box of a mysterious matrix, and in the end of the day, you'll spin out something that you want for prediction. But what is that middle thing? Sometimes it does not have a meaning. But you pay a cost for getting the statistical efficiency by risking stacking in local minima. You may not have a guarantee, if you run a poor heuristic such as EM on global convergence, and it is always slow. And these three are all mitigated, in the spectrum approach. Another kind of contradicting character is that people ask why, okay, this is so cool, why it is not everywhere yet? Well, you can see that the way I derive all these things is kind of painful. You need to really be familiar with the linear algebraic language and their operation, and also their hidden semantics, hopefully connecting to the latent variable theory. And these are all become explicit in the graphic model setting, because you can draw these bubbles as much as you want, and each of them has a meaning. Therefore, in terms of expressivity and the language or model composition, the graphical model or the EM view is really easy. It really makes it easy to derive new models. And in here, it's challenging to come up with a new kind of a procedure for a model that you haven't seen before. Okay. And it is actually unknown. It is even possible to do arbitrary inference on arbitrary loopy models. I don't know yet. It's an open topic. And a few other things on the numerical side. Well, here, because you are going to invert some matrices, and that's often a very dangerous practice. A matrix is, once you build it, you usually don't know whether it is invertible or not. Therefore, you may risk into numerical issues. But usually, what people do is to do it anyway by regularize it with a lambda times the identity matrix, just to make them full rank and invert it. Right? You lose some statistical power from there as well. This is the only thing shared on both sides. I don't know what's that. It's allowed for, conditional distribution. Yes, that's basically the language offered by our graphic model or linear algebraic way of writing down the joint distribution. And here we see a few more greens. It is easy to incorporate long-range features, and it is easy to generalize to the Hilbert space representation. Okay. All right, so that finished a block on non-parametric models and the linear algebraic inference algorithms. Next week, and actually this Wednesday, I'm going to enter yet another fancy topic in graphic model called the graph-induced structure sparsity. It is not quite traditional graphic model stuff, but in many recent applications, especially in genetics and in natural language processing, people find a need to express non-trivial constraints or prior knowledges to graphic model, to whatever prediction problems. So we're going to study how to deal with that. Questions? All right. See you on Wednesday then.